Hi. In the last video, I wrapped up the control logic midplane and got that off for fabrication. While I'm waiting for that to come back, what I'd like to do is focus back on the emulator and the breadboard build. Now, I have a fetch register on breadboard and I've had that fabricated already, but there's some issues here now. And what I want to do is I want to take a little bit, clean that up, see if I can use this or if I need to have it refabricated. Let's get into those details.
Hi, I'm Adam. I'm still building a 16-bit computer from scratch. I'm no expert here. I make lots of mistakes. So many mistakes I've actually had to reboot my computer build. I hope you will find my journey interesting, and I hope you will join me as I learn along the way.
I can hear you asking already. Adam, you've already got a fetch register on breadboard. Why not just go ahead and use it? Well, I've changed a few things since I designed this and had it fabricated, and I never got to actually populate it. But there's a few things that I think that I should call out that I believe to be issues that are going to be deal breakers here. First, let's take a look and see what this PCB actually looks like. I have a register here, a D-type latch, 74HC574, and that actually stores the contents and then hands that out onto an internal bus to a number of line drivers. Now, the line drivers themselves, one go to displaying the contents of the fetch register. 4 of them are asserting out onto different buses, ALUB, the main bus, address bus 2, and then the bus that goes from the fetch register to the instruction register. In the general purpose register design, I've changed that so that I eliminate the line drivers as extra ICs and instead latch each individual place that the data can go. The signals here are passed from the control logic, or used to be passed from the control logic, in the native format that the particular module expected. So since each of these asserts were active low signals, each of these signals came in as active low and then they were directly sent off to the individual ICs. In the general purpose register in my current build, I am passing these all off as active high signals, and these would need to be inverted if they were required on this particular module. So in other words, the main bus assert is an active high signal coming from the control logic, but because the assert control lines are active low, I would need to pass that through an inverter. The Silkscreen is not exactly the way that I had intended either. At some point I was using 4 bits for state and 4 bits to indicate what was going out onto the main bus, and then the remaining 8 were going to be the instruction. I realized very quickly that that severely limited the build, so I changed the upper 3 bits to be state and then 12 bits to be the instruction. And so the Silkscreen is absolutely incorrect and needs to be corrected. Finally, I had 2 rows of pins, one for inserting into the backplane that I was dropping this in, one for probing or putting additional signals up on top. And I have since chosen to abandon that particular configuration and only put the pins for dropping it in. Now, that will reduce the size of the board, and this is a single-sided populated board. I've got a few resistors and the like down here, but ultimately what I want to do is populate both sides of this so that I can reduce the size of this. If I'm going to reorder it, I may as well order something a little bit smaller and see if I can't reduce the footprint of this thing on my desk. That's where my head's at. I don't believe that this is actually going to work for me, and I could try to bodge something up, but rather than do that, let's take a look at it from this as a starting point, but let's make it match all of our other controls. For that, I now start with the emulator. Okay, Adam, what's your plan for this? Well, I'm actually going to use my favorite coding method when I'm in control of everything. And that is I'm going to copy and paste. What do I mean? Well, we have a module here called a general purpose register. And the fetch register, if you look at it in isolation, is really just a smaller version of a general purpose register. Instead of 6 entry points out onto buses, it only has 4 entry points out onto buses. It does not need a counter IC, it just needs to latch. So I can make a copy and start stripping things out that I don't need and let the compiler find all the different lines of code that need to be cleaned up. I think this will be a relatively quick process here. I'll be right back. Okay, here's the fetch register, and it's hooked up but doesn't do anything. So how do I test it? Honestly, to test it, I think I'm going to have to create a purpose-built test rig for it. Let me get started on that. So here are the controls. You can see my fetch register is loading. If I hit fetch suppress, it stops the fetch register from loading. That's working properly. Instruction suppress really shouldn't do anything because nothing should be hooked up between the fetch register and the instruction register. But when I turn this back off, you see that I get data now showing up here in the control module, which is a concern. It's not hooked up to the right thing. If it was going to be asserting, it should have been asserting right from the get-go. But you can see each nibble here is actually exactly the same. That's another problem. Address bus 2 appears to be working properly, and it's again a clock tick behind address bus 1, so that's good. ALUB, but that's also hitting main, and I believe that's because I still have an ALU that's actually working in the system, and it's also asserting out onto main, no matter what. And I say that because when I turn on main assert in the background back here, I'm getting errors that A bus has multiple signals that are asserted at the same time. So I've got a few things to sort out to get this stable, and not everything is actually directly related to the fetch register, but I want to take the time to get through it all. Okay, if I now assert out onto the main bus, I now am told that it is the main bus that has the problem. And quickly on the heels of that, if I now assert out onto main, the ALU is no longer asserting there as well, so I no longer have that conflict. Okay, so now if I toggle instruction suppress, which by the way, this is an issue, but at least I've got the address to look up in the control ROMs correct. Now, the problem here was actually in the control ROM control module, which apparently I didn't do a very good job of translating the code into a schematic. Each of these muxes was all looking at the same nibble of data. Now, I'm quite certain that I got this correct in the schematic and therefore on the PCB, but let's check it and be sure. Yes, and the data coming off the instruction are all distributed properly, not a duplicate of instruction 0. So I'm good there. The PCBs I just ordered are still good. Enough. A quick change to toggle those buttons in software, and you can see I am getting addresses up here to look up. Now, I'm getting also a large number of what would be instructions that appear to have the same value. I need to do some lookup on that, but moreover, if I turn off the instruction, or turn on instruction suppress, forgive me, it does not latch a 0 value here. This, on the other hand, could be somewhat of a big deal. I need to figure out why I'm getting zeros up here, but for whatever reason I'm not getting a latch. And I'm not exactly certain what that would be, so I need to kind of take a look at that and make sure that I don't have anything broken here in the PCB either. Yeah, this is working much better. So if you watch control ROM 4, instruction 0 has a value of 0, 1 and 2 have the value 9, 3, and then it reverts back to 0. So there's 0, 1, 2, and then 3. Control ROM 4 is behaving perfectly now. So this ended up being a problem with my implementation of the SRAM. in the emulator and nothing I need to worry about for the PCB. Now, at the same time, instruction suppress is also working properly now. Everything is showing up as a no-op instruction. Just the program counter increment is asserted. Okay, I'm in single step mode. I want to go through these one more time just to make sure that I am seeing what I believe I should be seeing. So when I assert out onto main, I get the contents out onto the main, and this is the source of that information. ALUB being asserted out onto ALUB, address bus 2, those are all correct. Instruction suppress, when I turn that on, the instruction, well, my instruction register stand-in goes to 0, or no-op, that's accurate. But if there's something else that's in here, such as this, if I do an instruction suppress, these are not supposed to change. They're supposed to only change on latch. So I've got a problem there. Now my fetch suppress really should be controlling the inbound into the fetch register, which means it's the outbound off the memory module onto the fetch bus. That should all be taken to null or 0 for a no-op. But when I step the clock, that should also latch a no-op, and it's not latching anything. So I've got that signal all messed up. I've got to go undo a little bit of that. And so this is the fetch register is latching with every clock cycle. All right, let me get those things taken care of real quick. Okay, that change saved me an IC, and I removed the fetch suppress signal here because I don't actually need it here. I actually need that as part of the memory module. So there's really nothing that's going to be done here. So you're always going to be latching whatever's being presented on that fetch bus, and I need to suppress the fetch at the memory module. Okay, so that's cleaned up. The last thing on the list to take care of was handling the instruction suppress. So the problem was when I toggled instruction suppress on, it was changing the contents of the control ROM latched values presented on the LEDs. And if I reset and go into single step mode here, I've got a no-op, it's 0. I step here, you can see I've got data on the control ROMs, but if I toggle instruction suppress, now it no longer hides the value of the control signals. If I am to step again, it passes on a no-op, and of course that's a no-op. If I was to turn instruction suppress off at this point, it still would not update those. That ended up being very good, but there ended up being a problem, and my line driver for the LEDs was positioned for the latch. So I had a problem here, and in the design in the emulator, I have the control ROM line driver, which is responsible for displaying the contents of the LEDs here. That was sitting before the latch. On the other hand, and I'm going to launch this here and get into the schematic, the line driver here is sitting after the latch. So the inputs here are bits 0 through 7. The outputs of the latch up here are bits 0 through 7. So in the schematic, it's sitting after the latch. I had to kind of finagle the emulator to get it to work. Now I'm going to log that as a bug that needs to be solved, but I'm not going to let it hold me up here. The breadboard actually matches what my expectation was for the schematic. The schematic is correct. The PCB order is correct. And of course, if I run into a problem, I'm going to have to figure out how I can bodge that. That then takes care of all the open issues except for changing the output from the fetch register to be the input into the instruction register, which hasn't been created yet. But I'm going to create a purpose-built bus just for that particular case and then get that wired up. Once I do that, all of this up here in the corner is no longer going to be operational. It's only ever going to show the no-op instruction. Let me get that done. Okay. And I've got my test code removed. I have my bus that goes from the fetch register to the instruction register set up, and I've redirected the control ROM inputs to come off the outputs from where the instruction register is going to sit. So I think I'm in good shape here. The only thing I could do above and beyond this is actually hook up the signals coming off the control ROM control to the appropriate program counter and the fetch register, just to make sure that those are being wired up properly. Let's do that. And that change does absolutely nothing to the user interface. So what have I done? I created a function called final wire up, and what I've got is all the different interconnects. I'm going to go from mid-plane to mid-plane. Now, I don't have a mid-plane built out for the registers. That is going to happen, but I don't have it yet. Before I can make use of this and actually expect anything to show up in the user interface, I need an instruction register and I need program memory. Okay, I think this wraps up the emulator portion, so let's start looking at the schematic and figuring out what we need to do there. Here's the schematic for the current fetch register. It needs to be pruned down a little bit and cleaned up a little bit, and I believe I'm going to end up with a slightly simpler circuit, but we need to start by taking care of some of the things that need to go away here. For example, I had put sockets on everything, and the reality is I don't need those sockets. I thought it was going to be a little bit easier for testing to have the sockets available. I've since realized differently. I have several signals, control signals, that need to be brought in, and so I want to take a minute and look at those. I want to take a look at the naming convention I used for the pins and make sure it matches the code. Now to update the control and power input pin counts. Next, I'm going to change all of the line drivers to be latches. That's a relatively simple change to make, but one of the line drivers needs to remain a line driver, so I need to circle back to that and change it back once I'm done. It's the shortest distance between 2 points. I add the inverter. Next, the inputs to each of these latches needs to come off the fetch bus. Each latch needs a copy of the clock. Now for the line driver, which is responsible for displaying the control signals. Now for the pull-down resistors. I double-checked the breadboard and they use 10K resistors, not 1K resistors, so I'll make that change here. I also believe that they should probably be passive signals, not active input or output signals. So I'll make that update as well. After some quick organization, I'll sort out the inverter and get those signals routed properly as well. Now for some cleanup. I'll start by drawing some boxes around stuff and trying to organize things a little bit so it reads just a smidge easier. I think I have enough room I can cut the page in half. Let's do that. Okay, next I'm going to run the electrical rules check just to make sure that I've got everything handled properly. I should actually go through and redo the references as well, make sure that everything's updated. And then electrical rules check and clean up any issues that I've got here. So reset is not connected. And reset hold is not connected. Now I doubt I can do this. I honestly do not expect this to work, but let's give it a shot. Yeah, that's what I thought. Let's name the signal. Get rid of that, and we will drop in an unconnected there. Now that I do expect to work. Except I have it in the wrong spot. Alright, so I need to do the same thing here. Fetch bus. And that needs to be here. Wonder if I can rename all of those. Alright, let's try this, because I believe I can do this. I can hack my way through it. In case you're wondering what I'm doing here, I'm using Find and Replace in my favorite text editor. Alright, let's see if that works. That all looks good. Let's try this again. Okay, where's my easy button? Alright, so now it's just a matter of grabbing the code and walking through a hard copy of this with the code and making sure that everything actually ticks and ties properly. I'm going to spend a few minutes on that off camera, and I'll come back and report the results. The only difference I found here was the sequence in which each of these signals are wired up here. And on the emulator, they go from bit 0 on pin 2 to bit 7 on pin 9. And here I've got bit 0 on pin 9 and bit 7 on pin 2. So do I need to go back to the emulator and clean this up? And I don't think I'm going to do that. I think I'm going to leave it as it is because it's just busy work for me to actually do that. I don't think it's going to make that big of a difference. It makes far more logical sense here to have it ordered the way I do in the schematic, and far more logical sense to have bit 0 refer to bit 0 in the emulator, not having those reversed. One is a naming association, that's in the emulator. One is a positional association, and that's here on the schematic and on the breadboard and ultimately on the PCB. So everything else turned out okay. So now it's just a matter of cleaning up the PCB design. Okay, I had a bit of a choice here. I could work on the PCB or I could work on the breadboard. I chose to go the route of the PCB and wrap up all the KiCad work. I'll deal with the breadboard likely in a separate video. So here is really what the last iteration was, and if I remove the fill, you can see kind of how this is laid out. Now if I go and try to update from the schematic, I expect a whole lot of things to break, and I'm likely going to have a whole lot of things that I need to actually reroute, and that's kind of where I'm at right now. And I've actually got a few that have no footprint, so I actually need to go fix those. So let's see here. I don't have a footprint for this yet. Okay, let's try that again because I am expecting at least that to show up. There we go. There's the one I'm looking for. There's the 04. So I'm betting if I go and I clean up my traces, a whole bunch of this also gets removed. And I'm almost back to square one here. That footprint is incorrect. Let's just remove all tracks and vias. Okay, so here I've got, basically I'm starting over here. My limiting factor here is going to end up being the header pins, which are going off board. And I've got a lot of those I need to kind of sort through and get organized. I'm certain I'm going to be able to reduce the size of this. Certainly by putting things on the back as well. Yeah, I am quite tempted to really start this over here. I want to leave the cutout the correct size because I want to be able to see how much I'm able to reduce this by, at least for the moment. The natural or typical input and output here is from the fetch bus to the instruction input. And so I want to do my best to kind of work that into a straight line here on the board. Not all the pull-down resistors survived in the same location, so I now have to reorder those. I'm going to move the resistors to the front layer. With the latch on the back layer, it's just a good use of space. And with that, I take the time to line them up with the pins as best I can. Those resistors need a via to the ground plane, so getting the IC placed correctly makes that routing easier. Next, I want to bring in the LEDs and their resistors. Now for the signal LEDs and their resistors. And now I grab the latches for the contents LEDs. Next, I grab two of the bus outputs coming off the fetch register. If I'm careful, my plan is to be able to stack the latches on top of each other. The inputs being on top of each other should really be able to be connected with a via right there at the pad, and then the outputs directed immediately to their respective pins. Okay, it is at this point that I can very easily convince myself that I have quite a bit of opportunity to collapse this into a smaller footprint. I have lots of open space down here. I have lots of open space left and right. I have the ability to collapse these two front and back ICs to make them take up less space, so this bottom edge can come up probably, I'm thinking, well, I don't know exactly what that's going to be. Might be a good 20 millimeters. First order of business here is I want to try to collapse this left side of the board here. I believe I've got lots of opportunity to do that. I need to squeeze two capacitors in there. Okay, now let me move this down and get it lined up properly. Okay, now those are going to be too close together, so let's stretch those out just a little bit. Yeah, I think that'll work. And that's as dense as I can get that section. So I'm pleased with that. Okay, first order of business here. Well, let's move this out of the way because I'm ultimately going to want that up here somewhere. And let's see if we can collapse these two ICs here a little bit better. Okay, let's see what we can do with these two ICs and the LEDs. What have I done? Hang on a second. I've got this all messed up here. Let's revisit this. All right, so to make things a little bit cleaner, I want to swap instruction suppress and ALUB on this bus. I want to flip those, and then I want to flip those. Now on this one, I want to move all of these signals from the ground side to the VCC side. So one goes to 6 and etc. all the way down. That should be able to go there. All right, I think I'm going to move these to the back. Okay, I'm officially so dense I may not be able to fit the text in. Okay, so why is this version 2.0 instead of version 1.1? The short answer is because I completely changed the interface. Both the pin positions and the signaling have all changed. And by semantic versioning, we increment the major version number. Now I've just got a few more things to deal with here. So let's shrink the footprint now. I want to do this in multiples of 1/10 of an inch. Oh, that ain't gonna work. Try that again. Okay, once again, I don't have the room I need for all the Silkscreen. At this point, I want to route and make sure that I can actually get everything routed. I'm very confident that I can, but I just want to go through that process. 357 unrouted traces, and then I will work on getting the Silkscreen dialed in for this after that. Okay, before I get into routing, I realized that I forgot to add a few things to the schematic for bodging if I decide I'm going to do that. So let me see if I can get this cleared up here. I think I'm ready to route this. What I'm going to do is just put my head down and knock it all out. Okay, well, compared to the control logic mid-plane from the last video, this is actually a relatively simplistic route. There's not a lot that's really going on here. Taking the time to stack the signals on top of each other where they were the same on the top IC as the bottom IC, updating the schematic and the like, really actually paid off because it ended up giving me a 2-for-1. I route one signal and I get 2 connections out of it. Other than that, it's really very much a very simplistic route and it comes together very easily. That leaves me with just Silkscreen left. Front Silkscreen. Let's see what we've got here. I know I've got a bunch of overlap and there's a whole bunch of stuff that's off this side of the PCB. So I'm going to have to work on getting all of that stuff kind of moved and rearranged and tucked in here. So where do I start? Oh, this is facing the wrong way. Okay, I'll go through this rather quickly. I'm missing a number of things. I have to come back to it in the end and revisit all of this, so you're going to get a second look at the front side of the PCB. In the meantime, I work on trying to get the Silkscreen dialed in as best I can. It all changes here in a minute. Okay, let me get smart and hide the copper layer. Okay, let's flip over to the back side and start working on that. It's really a lot more of the same, but I've got a trick up my sleeve here in a second. Well, I found a new tool, and this tool should allow me to relocate all of my reference designators on the back fabrication layer to the back Silkscreen and change its text attributes and undo the keep upright, make it visible. Well, let's see what happens. That looks like it worked pretty well. That is likely to save me a whole lot of work. Now, I guess the next question is can I change its reference point? No, can't change the reference point. So I'm going to have to get in and do that, but that's easy enough to do. Yeah, that's going to work much better. Now I have to jump back to the front to take care of the Silkscreen there. There's a lot of things that happened as a result of changing all the text all at once, but it's a small price to pay for the amount of time I actually saved overall. Nice tool. All right, let's save that. Let's run the check again. Okay, nice. Okay, this was a huge step towards being able to execute code in the emulator. I also need these for the build, and I'm going to start working on putting together another order for fabrication. Ahead of recording this wrap-up, I rendered and watched the video so far, and there are 4 things that may end up coming back to bite me, and I've got those captured as things that I need to revisit before I actually commit those PCB Gerbers and send those off for fabrication. I want to make sure I tick and tie everything before I order something that's just going to end up in the trash. So what are they? The first one goes back to the emulator, and I touched on it briefly in the emulator section, and that is that there's some code that's not actually working right when copying the control ROMs quickly. And so I need to go back, revisit that, make sure that all of my signals are correct. And I'll likely have to spend some time going back and forth between the breadboard circuit, which does work, and the emulator, which does not. Something's still not right there, and the problem, I believe, to be in the emulator, not with the circuit. The second issue is that in single step mode, the fetch register is not reliably staying 1 clock cycle behind what's being presented out onto the bus from the program counter when I had that test rig set up. Now this may or may not be an issue, but I've got to redo that test rig, get it set up, and make sure that that is actually working properly. Again, that one may end up influencing the actual design of the circuit. So I need to get that buttoned up before I can send those PCBs off for fabrication. Next is actually a complete error in the schematic. I totally missed this, and I left the control signal LEDs hooked up to VCC. So those LEDs are going to be turned on when the signal is not asserted and turned off when the signal is asserted. Well, that's actually absolutely wrong. Totally backwards, and I need to get that fixed. And finally, the fetch register pull-down resistors, so the ones for both the fetch bus and the instruction bus that leads off into the instruction register, they're inconsistently located, and I want to think about exactly where those should be located. I've got a couple of choices. Now, these are buses that have a point A and a point B, and there's really not much other than the source and destination that are connected to them. But I need to decide if I want to, at the source, if there's nothing asserted, default the signal low. At the destination, if there's nothing coming in, protect itself with a default low. Or put them on the back plane or mid plane and take them off the individual components altogether. So I will come back to that and revisit that in another video as well. I want it to be topical, and I don't want to just pile it onto the next video. So look for that in the upcoming video, but in the meantime, the next thing for me to tackle is the instruction register. I want to get that set up so that I can legitimately start executing code. We'll see you soon.